Today, I would like to talk about differentially oblivious database joins. This is joint work with Hubert Chen, Shumo Chu, and Danyang Zhuo. Imagine a scenario where one wants to outsource a sensitive database, for example, containing medical records, to an untrusted cloud server. The data is encrypted to protect the patient's privacy. Now, a doctor would like to make queries to the encrypted database. So how can we support queries on encrypted data? There are multiple approaches, either relying on trusted hardware or relying on secure multi-party computation. In this talk, imagine we use trusted hardware, such as Intel's SGX. Trusted hardware essentially creates a hardware sandbox such that data can be decrypted inside this sandbox and computation can take place. Moreover, any data or computation result that ever leaves the sandbox will be encrypted again. This way, the untrusted server cannot see the data contents in the clear. With such a secure processor, we can build what's called an encrypted database. You might have heard of systems like CryptDB, TrustDB, and so on. And these works essentially provide encrypted database systems. And they are also what I call the first generation secure databases. I mean, of course, not all of these systems look exactly like the picture I've shown here. And they use, somewhat different techniques, but this is kind of like a high level picture of what's going on. The point is, these encrypted database systems have been broken left and right in numerous follow-up works. Some attacks even showed how to partially or fully reconstruct the database. An important reason is that it's not enough to just encrypt the data. It's well known that access patterns to even encrypted data can leak highly sensitive information. Here, by access patterns, I mean the sequence of memory addresses the program visits during its execution. To defeat such access pattern leakage, recently there has been a new line of work on the second generation of secure databases, essentially oblivious databases. Notable examples include ObliDB, which came out of a Stanford group, Opaque and Obladi, which came out of folks at Berkeley. So what are oblivious databases? To understand oblivious databases, let me actually explain what are oblivious algorithms in general. Oblivious algorithms were first proposed by Goldrick and Ostrovsky back in the 1980s. At a high level, an oblivious algorithm is capable of obfuscating its own memory access patterns. Moreover, it provides provable guarantees of privacy. Somewhat informally, oblivious algorithms have the following security requirements. Basically, the access patterns must be independent of the secret inputs to the program. In the case of database systems, the secret input would just be the database itself. The way I like to think about it is that the access patterns are as secure as encryption. Throughout, I'm assuming that the data is always encrypted, but with oblivious databases or with oblivious algorithms, the access patterns would be quote unquote encrypted as well. At first sight, this seems unintuitive and almost magical. We can encrypt data that live as bit strings. How can we encrypt access patterns which are a side effect of a program's execution? Let me reassure you that indeed this can be accomplished using algorithmic techniques. There's actually a line of work dedicated to this topic. In summary, we know that we can make any program oblivious while preserving its functionality with only a logarithmic slowdown. Moreover, the logarithmic slowdown is unavoidable due to a well-known lower bound by Goldrick and Ostrovsky. So it seems like this would be the end of the story. Like we have tightly matching upper and lower bounds. We can use non-oblivious algorithm techniques to build oblivious databases, achieving only, roughly speaking, logarithmic overhead. Okay, so is it really the end of the story? As it turns out, the real picture is not as rosy as it may seem. To get this logarithmic overhead, all prior works actually make a tacit assumption And basically, it's okay to leak the runtime of the program and the result length. For some computation tasks, this is not an issue because maybe the runtime or result length are fixed and they're not data dependent. But in other cases, the runtime and the result length are indeed data dependent. And in these cases, if you want to have full obliviousness, you have to pad the runtime and result length to those of the worst case input. And for some tasks, such padding, they don't incur a big blow up. However, I want to convince you that such worst case padding can be hugely expensive in real world scenarios. So back to our secure database example, in real world databases, a frequent operation is database join. So here's an example of a two-way database join. We have two input tables on the left. I want to join these two tables using the key department. So what a join operation does is that for each distinct key, it'll take the Cartesian product of the entries in the two input databases with that particular key. In this case, the join result is shown on the right. And again, remember we are taking the Cartesian product for each key here. So now imagine the input tables have sizes n1 and n2, respectively. In the worst case, the result size can actually be n1 times n2. In general, the two input tables need not have the same size, but for simplicity, for the rest of the talk, I'm going to assume that they both have size n. And in this case, the result size can be quadratic in the worst case. We also know that in real world databases, the worst case almost never happens. And for most common database join queries encountered in practice, the result length is typically linear or quasi-linear in n, rather than quadratic. However, if we insist on full obliviousness, we have to pad the runtime and result length to the worst case, basically quadratic, even when the actual length may be linear or quasi-linear. So this actually means a polynomial blow-up in performance, not the commonly believed logarithmic blow-up. When the database is large, let's say several hundred gigabytes or terabytes, there's actually a big difference between a quadratic time algorithm and a linear time one. So to summarize, in some cases, fully oblivious algorithms can incur actually polynomial blowup due to the worst case padding and not the commonly believed logarithmic blowup. Indeed, prior oblivious databases were confronted with this problem, and to avoid this worst case penalty, some works choose to allow arbitrary length leakages. Of course, this is going down a slippery slope, right? If you allow arbitrary leakages, it basically means no provable security guarantee. The question we care about answering is, can we achieve number one, meaningful and quantifiable privacy? And number two, good instance specific performance. So ideally, the performance of the private algorithm should be close to the instance specific performance of the original insecure algorithm. And this brings us to the notion of differential obliviousness, originally proposed in our earlier work that appeared in SODA 2019. At a very high level, differential obliviousness means applying the notion of differential privacy to access patterns. And I'll explain this in a bit more detail later in the talk. The plan is the following. First, I'll introduce our results. Next, I'll quickly revisit the definition of differential obliviousness. And then I'll talk about our differentially oblivious algorithm for database join. So let me first tell you our result. Throughout, I will use the letter N to denote the input size. The letter R denotes the output size. So we know that the best insecure algorithm takes time R plus N. You can achieve this using efficient hash tables. And this is also the best you can hope for, because just to write down the result would take R time, and just to read all the input would take N amount of time. On the other hand, we know that if you insist on for obliviousness, you would have to suffer from the worst case cost, which is quadratic. So we show that with differential obliviousness, we can almost match the performance of the insecure algorithm. Specifically, we can achieve R plus N times log N runtime. And essentially the result size is R plus some extra padding term. And that's roughly M times log N, where M is the frequency of the most frequent key. So again, M is the frequency of the most frequent key that appears in the input. We also prove a lower bound, essentially showing our upper bounds are nearly optimal in some sense. I won't go into the formal statement of the lower bound because I want to focus on the upper bound in this talk. So with this, let's quickly revisit what is differential obliviousness, and then we can talk about our algorithm. So what's differential obliviousness? Imagine we have some database, we are running some data analytics algorithm or running some query on the database. The algorithm will visit some memory locations and where the database is stored. And the sequence of addresses visited is called the access patterns, right? So here, remember, we are assuming the data is encrypted. So the only thing the adversary is observing is the access patterns. Now consider a neighboring database. Essentially, I'm changing only one entry in the database from the blue one to the red one, and every other entry remains the same. And I'm going to run the same algorithm on this neighboring database, and I see some other access patterns. We want that the distribution of the access patterns on any two neighboring databases be close. Specifically, I have to tell you how to define closeness. And essentially, we adopt the same closeness notion as in the differential privacy literature, basically as shown in the equation on the slide. In other words, consider the probability of the blue access patterns being any set S, and the probability of the red access patterns being in the same set S. We want the two probabilities to differ by at most a multiplicative factor of e to the epsilon, and additionally tolerating an additive delta difference. So this is essentially the notion of epsilon delta differential obliviousness. For the rest of the talk, we are going to assume epsilon is some constant, and delta needs to be some negligible function in n, which is the input size. And these are basically the typical parameters we use in this line of work. Okay, so now we are ready to see how the scheme actually works. In the interest of time, I'm actually going to tell you only a warm-up scheme that achieves a slightly worse asymptotical performance than the one I claimed earlier. We'll need some extra clever tricks to get the final result I mentioned earlier, but I don't have time in this talk. You have to read the paper for the details. So how does our algorithm work? Remember, the input is two tables, the blue one and the green one. Without loss of generality, I can assume that each table is a list of key value pairs. And we want to join the two tables based on the key. Remember, joining is essentially computing the Cartesian product for each key. So the first thing I want to do is to write down what's called a noisy count array. So basically, for each key that appears in at least one input table, I want to write down how many times it occurs in each of the input tables. Further, we will add a positive noise to the true counts to obfuscate these numbers. To make sure that the length of this array does not leak information, we just have to pad the array with some filler entries at the end to a fixed length of 2 times n. These entries have fake keys. So these filler entries, they have fake keys that don't actually exist, right? So their true counts are actually 0. So but after we add this positive noise, and you actually see some non-zero values. And so we want to make sure, we want to generate this noisy count array, but we want to make sure the algorithm's access patterns do not leak information. So therefore, we rely on oblivious algorithm techniques, such as oblivious sort. Also, remember I mentioned we are adding some positive noise to each true count. And here we are using standard differential privacy techniques. We're adding noises that follow a Laplacian distribution, but shifted to the right. So the noises are always positive, except with negligible probability. And later on, these noisy counts will actually be revealed through access patterns. And that's why we care about protecting them with noise here. So I won't go into the details of the oblivious algorithm, right? But I'm just going to ask you to trust me that using oblivious sort, we can indeed write down this noisy count array. And the step will take quasi-linear time. More specifically, it takes roughly n log squared n time. So next, we can arrange, we want to arrange the items in the input tables based on their keys. So for example, for the first key K1, the blue bin stars items coming from the blue table with the key K1, padded with filler entries to a total capacity of 8, where 8 was the noisy count we wrote down earlier. So the shaded area, means filler entries in this picture. Similarly, also for K1, the green bin stars items from the green table with the key K1 padded with fillers to a total capacity of 6, where, remember 6 was the noisy count we wrote down earlier. And we do this for each and every key. Basically, we will write down 2 bins for each distinct key contained in the noisy count array, including the filler keys. So at the end of the step, all these noisy counts are revealed because the sizes of these bins are revealed. Again, we want to make sure that the step doesn't leak anything more than all these noisy counts through the access patterns. So to achieve this, we again leverage oblivious sort. I won't go into details here, but just take my word for it. If we have oblivious sorts, with constant number of oblivious sorts, we can write down all these bins, and it will take quasi-linear time to do this. And more specifically, it takes time n log squared n time. Finally, once we have these bins, we just compute the Cartesian product within each key. So when we compute the Cartesian product, if at least one entry is a filler, then the Cartesian product result will also be a filler. This step is actually performed non-obliviously. And essentially, we just scan through the blue bin and the green bin in a coordinated way and to take the Cartesian product. And the only thing it reveals are basically the bin sizes themselves, which are basically the noisy counts. So that's the high-level idea. I didn't spell out how to use oblivious algorithm tricks to accomplish each step. And the key insight in our algorithm is that essentially when you are taking the Cartesian product of each key, you want to make sure you only reveal these noisy counts. And these noisy counts are protected with differentially private noise. And finally, we also need to be a little bit careful and hide the total number of distinct keys. But we are just doing that with padding. It's not too hard to show that this entire algorithm takes time r plus n log squared n. Recall r is the true output length. But remember, our final result is actually r plus n log n, right? With the log n factor smaller. And to get this final result, we'll need some additional tricks. And I don't have time to cover them. So to just read the paper for the details. That's the idea. It should be quite intuitive, but in fact, there is an important subtlety that I've neglected to mention so far. And the subtlety is actually critical to the privacy of the scheme. Recall in the first step of the algorithm, we need to write down this noisy count array. And here we need to make a decision. We need to decide in what order are we going to store these keys. So remember later in the algorithm, when we place these elements into bins, right? We are revealing these noisy counts during that step, and these bins will actually follow the same order. So there are two natural options. We can sort them based on the keys themselves, or we can sort them based on lexicographical ordering of the noisy counts. So now I'm going to ask you to think, which of these two would you pick? If you think about it carefully, you'll realize that basically the first one would completely violate our privacy requirement, whereas the second one would be okay. And here is the reason why. Imagine, we sorted the noisy count array in increasing order of the keys. And like I said, this is completely broken, and I want to tell you why, right? So consider two databases that are neighboring. In both databases, the keys K1 through K7 appear 100 times in each table. In the database on the left, the largest key K8 appears once in the blue table, and it doesn't appear in the green table. In the database on the right, the single item with the largest key K8 is replaced now with K0, which is like the smallest key. And again, it appears once in the blue table and doesn't appear in the green table. So now if you were to run our algorithm, during the step in which the noisy counts are revealed, and that's when we place these items into bins, with significant probability, you'll see that, in the world on the left, essentially the light bins will occur at the very end, whereas if we live in the world on the right, then the light bins will occur at the very beginning. And using this observation, we can basically differentiate which world we are in with significant probability. So the way to fix this problem is to basically sort the keys not based on the keys themselves, but based on the noisy counts, which we are going to reveal anyway. And in fact, if we did that, then we would be able to formally prove that the algorithm indeed satisfies epsilon delta differential obliviousness. To summarize, I've told you that, in real world applications, for obliviousness sometimes incurs polynomial blowup and not the commonly believed logarithmic blowup. And this comes because of worst case padding. And differential obliviousness allows us to overcome the worst case curse of fully oblivious algorithms, and we can achieve good instance-specific performance. I told you about a warm-up algorithm that achieves differentially oblivious database join. The algorithm blends techniques from oblivious algorithms and differential privacy. There are several other results in the paper that I just didn't have time to talk about at all. I didn't mention the extra tricks that lead to the improved algorithm. In our paper, we actually also analyze our algorithms using a more realistic efficiency measure called cache efficiency. So this is actually the measure you ought to be using if you were to implement these algorithms on secure processors like Intel SGX. So I just didn't have time to talk about this at all. I also didn't have time to talk about lower bound proofs. So you'll have to read the paper for more details. Thank you very much.